Good morning everyone, I'm Terje, and today I will show you how to set up and run 4 different solvers for transient dynamics. And I will use an example from a previous machine element exam from 2009, which is a quite simple suspension system, a torsional beam representing most of the flexibility, an arm which is quite rigid, and a wheel hub representing most of the mass. I will show you how to set up and run the SOL109 RS solver, which is modal, and then to set up and run the SOL112, which is also a modal solver. And then I will run SOL109, which is a direct solver. And I will also show you how to set up and run the FEDEM solver, which is direct as well. Then I will compare the results from the various modal and direct solvers with respect to speed and accuracy. This is how the trailer suspension model is illustrated in the exam. We have this torsional shaft, the beam, and the wheel hub. And here is how it's modeled in NX. We have this torsional shaft, which represents most of the flexibility, and this beam, rather stiff, and the wheel hub. And in the center of the wheel hub, I have applied a load, which is controlled by this excitation function, which is a half sine with a frequency of 8 Hz. And that is pretty close to the first and lowest eigenmode of this system. And we are looking for a response like this. In NX, you have different solvers to choose between when you do transient dynamics. First, you have SOL109 RS, and then SOL112, which I will run, and then I will also show you how to set up and run 109 and FEDEM as well. In the exam, the students are asked to calculate the vertical displacement for a static load of 2,940 newtons. And the exact solution is 76 millimeters. What I want to show you is how you can calculate the dynamic amplification factor, the DAF factor, for these solvers. And the DAF factor is given by the maximum dynamic displacement divided by the max static displacement, which is 76. So for all these solvers, I will give you this DAF factor, and let's see if they are matching or if you have any deviation. And also I want to show you the amount of time it takes to set and run the different solvers and to execute them. So stay tuned. This is the finite element model, and it's an assembly FEM consisting of 3 different component FEMs meshed with solid elements with steel properties, and the individual meshes are connected with phase gluing commands. In addition, I have 2 concentrated masses, one 5 kilos mass applied here, and another one 8 kilos mass applied in the center of the wheel hub. And this is the FEM model used in all simulations I'm going to show you now. Here you can see I've created one sim file for my assembly FEM. And in my sim file, I've defined 3 different solutions. One for the SOL109, one for 112, and one for 109. When I do it like this, it's easy for me to reuse the simulation objects, the gluing, the constraints, and the loads. And then I can be sure that I'm comparing results for identical models. Let's first start with the SOL109 RS solver. Here you can see my SOL109 RS setup. I've created a solution based on the standard setup, SOL109 response dynamics. Then in my dynamics subcase here, I requested 10 modes, 10 eigenvalues. That's all. Then I can run the simulation and I get information about the mode shapes. And here you see after that, I've created a simulation or solution sequence called Response Dynamics 1. And then I will have access to the modes, information about the modes. By the way, I can also quick view them from here. And here you see typically mode number 1. However, the most interesting stuff is in the response dynamics details view. And here you see that I have a mass participation factor in the Z direction of 78.56 for mode number 1. And you can see that mode number 6, 7, and 8 also have a participation factor of more than 0.5%. And that gives me a mass representation in the Z direction of 95 or more, which gives me a quite accurate modal-based model. Then I've applied damping, viscous damping, which is roughly 3%. And that one is calculated based on the structural damping in the corresponding direct solvers. And I will show you that later, how it's calculated. When I've activated these 4 modes, I'm ready to create an event. And here you see in this event, which is a transient event, we can check it here, mode displacement. And here it's important to add user define as the duration option, and duration time I've set to 1 second for all simulations. If the option is excitation function, you will have results just for the time period where the excitation is working. And the initial conditions are set to 0. This excitation, we can have a look at it. It's described in the Z direction. It's a half sine, nodal force, and the node is in the center of the wheel hub. And as you can see here, I've applied a transient load function. I can go to the function manager, which is called SOL109 excitation. That one is scaled, has a maximum peak of 1. And I want to compare the dynamic results with the static results. And my static load was 2,940 newtons. So that's why I scaled this function with this factor. Another thing is that in order to create this function, it can cause you some trouble because you have to use some Java software to do it. And then you can create it by using the following command. First, you should check that you use these override Java setups, which describes where the Java software, the runtime environment is located. That's an important one. And you should also check that it's actually running. You can also do that with file, execute, and check Java for NX. And this one is approved. Then you can go to the menu, you go to tools, you go to response dynamics, function tools. And then you get access to this menu, this Java menu. And here I used the pulse option in order to create my excitation. So that's how I did it. Let's go back to the application pre and post. So here's my excitation and my transient event and my modes, which represent my model. And what I now will do is to calculate first the modal amplitudes for these excitation functions, and then NX will retrack the displacements for all nodes. But in this case, I can ask for just one node, and I can run evaluate function response nodal. And I can select the node to be this center node in the wheel hub. That's the one. And the Z direction. And then I press OK. And then I can have a look at my function. And here is how it works. You see, I calculated my logarithmic decrement based on these amplitudes, which gave me the viscous damping that I wanted, and which corresponds to the structural damping of 6%. And here I can request my peak. And here you see it's roughly 104 newtons. And based on those results, I calculate the dynamic amplification factors for the various modal solvers. So this completes my presentation of the SOL103 RS setup. Then I've activated my modal transient solution, the SOL112 solution. And let's have a look at the setup. I have in case control added one output request. I request modal effective mass. And you should know that when you use this solver, you will not have access to the mass participation factors in the user interface. They will be printed to the FO6 file. So you have to check it out in order to select the right modes. But we already know those modes because we have been running the SOL103 RS. And then I've requested 10 modes from Lanchos. And in the modals selection, I've selected 1, 6, 7, and 8. Those are the modes that we identified in the SOL103 RS solution. That's it. And then in my subcase, I've selected my setup for the mode selection and structural output requests. And in addition, I've applied 6% structural damping, which matches the viscous damping I've applied in the SOL103 RS. Then I can check my results. It takes some minutes to run this one, so that's why I'm not showing it live. And here you also see that I have access to the results from the different solvers, which makes it easier to compare. And there is my SOL112 solver. And here we have the displacements. Let's select the displacements for the first increment. Then I want to create a graph. And I select my entity, which is the center node in the wheel hub. And I extract the results from that center node. And this takes some time. It scans through 201 iterations and select the displacements for the requested node. Then I will have access to the plot. And these are the results I'm looking for. Here I can request the peak, as I did for the SOL103 RS solution. And you see I have a maximum amplitude here, displacement amplitude of 111.2 millimeters. And based on that one, I'm calculating the dynamics amplification factor for this solver as well. And at the end, I will compare it. Then let's have a look at the direct transient solution SOL109 setup. It's now activated, and I can check it out. Case control is set as default, and the solution type is SOL109 direct transient response. And in bulk data, I've applied structural damping, 6% structural damping, and the dominating frequency is 8.12 Hz, which is the lowest mode of my system. And this damping is representing also this viscous damping I used in my modal analysis, which was 3% roughly. Everything else is just as default. Then in my sub case, direct transient, I can show you here. Here I've specified the time interval. And this is the same time interval as I used for the modal transient solution in SOL112. Let's have a look at it. You see I've selected a time increment of 0.005 and 200 time steps, which give me a total time period, simulation time of 1 second, which matches the modal solver's setup. And I want to have the results for each iteration or increment. So that's my setup. When you run a direct solver, NX is calculating all the nodal displacements directly and not the modal amplitudes, and then after that retracting or calculating the nodal displacements based on the modal amplitudes and mode shapes. So let's have a look at the results. Okay, here we are. Direct transient solution SOL109. Let's select the first increment, the set displacement, and let's create a graph. We select the same entity, the center node in the wheel hub, and then we request the results for each time increment. Lots of results to load. There we are. Let's plot the curve. And here we see the results. It looks quite familiar, I guess. And let's have a look at the peak value here. It's 109.6, really close to the modal solution. And based on this value, I'm calculating the dynamic amplification factor for this direct solver as well. And after the FEDEM solver is completed, I can show you the comparison of all results. Here is the FEDEM model, and we have imported here the same finite element models, the component FEMs that we used in the assembly FEM in NX. The damping is the same, although I have not applied the structural damping as I did in the direct solver in NX. Here I applied the corresponding stiffness proportional damping that gives me 3% viscous damping. And so it's the same damping, and also the stiffness is the same because it's the identical meshes. And I've also applied two concentrated masses, 5 kilos and 8 kilos. The function I'm using to put the excitation on the wheel hub is shown here. It's a half sine with a peak at 2,940 newtons, which was the static load in the exam. And then the frequency is 8 Hertz, so it's identical to the excitation in NX. Then I can load the results, or I can load the animation. I can load the graph like I did here, and then I can simulate the suspension in FEDEM. The stop time is the same as in NX, 1 second, and the time increment is the same as in the direct solver in NX. So let's run the simulation. There we are. The elapsed time is 2 seconds, and the CPU time is less than half a second. And the secret is the model reduction applied to these models. And here you see the results. You can also load the animation. And let's check the maximum peak displacement. It's 110 newtons. Oh, sorry, millimeters. And this value is used to calculate the dynamic amplification factor of FEDEM as well. So that concludes my simulations, and now let's have a look at the results and compare them. Here is a summary of the results. The dynamic amplification factor is set to the maximum peak displacement for the dynamic simulation divided by the static deflection when you load the suspension with 2,940 newtons. The dynamic amplification factor for the SOL103 RS was 1.31, and for the SOL112, which is also a modal-based solver, was 1.46. So SOL112 gave us a higher amplification factor, which is a bit strange because I've selected the same 4 modes to represent the structural flexibility for both examples. Then the direct solver SOL109 gave me a dynamic amplification factor of 1.44, which is very similar to SOL112, the modal solutions. Then FEDEM gave me a dynamic amplification factor of 1.45, which is quite identical to these two solvers. The main difference is the simulation times, and here you see the SOL103 RS was quite fast with an elapsed time of 34 seconds. The SOL112, which is also a modal solver, was 2 minutes, and the direct solution took 6 minutes. And also FEDEM, it's a direct solver, but the elapsed time there was only 2 seconds. It's not really fair to compare these numbers because SOL109 RS is calculating the mode shapes in advance, and FEDEM is calculating or doing the model reduction in advance. That means FEDEM is doing the component mode synthesis, so during the simulation FEDEM is only calculating the displacements in the triads or supernodes. That's why this one is extremely fast. It's designed for mechanism simulations. This solver is calculating the mode shapes while before it's actually doing calculating the modal participation factors. Both these two solvers, they will calculate 4 independent equations representing the 4 modes, and then calculate the amplitudes of the mode shapes for each time step, and then multiply these 4 amplitudes for each time step with the mode shape or eigenvector. And then these are superimposed, and that gives the complete or overall displacement in all nodes. So it's completely different algorithms. But you see the results are quite comparable. I can't really explain why these two results deviate so much. The same modes are used. It might be that the excitation function in this example is a little bit smoother than for these two. But that concludes my presentation of the different solvers. Now we have seen how you can set up and run the different solvers and to show the results, the curve plots. And my recommendation is that you, if you don't have too many time steps, you could run the direct solvers. They are always reliable. They don't depend on the selection on the proper modes. But again, the penalty is simulation time. So that concludes my presentation of transient dynamics, and thanks for watching.